Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into the mysterious world of black holes, those silent shapes scattered across the universe that seem to swallow light itself. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe. Only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into black holes together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. Imagine for a moment a place in the universe where even light cannot return. Not because something is chasing it or pulling it back, but because the very idea of away no longer exists in the way we expect. A place where directions begin to blur and where time itself seems to loosen its steady grip. Black holes are often described as cosmic traps or deep wells in space where everything falls inward. But that picture, while not entirely wrong, is only the beginning. Because black holes are not just things. They are not simply objects floating in space like stars or planets. They are more like questions, written into the fabric of reality itself. And the deeper you look at them, the more those questions begin to whisper. For a long time, physicists believed they understood the universe quite well. They had built two great ways of describing nature. One of them tells the story of gravity, the slow, graceful bending of space and time like a stretched fabric gently curving under weight. The other tells the story of the very small, the restless, flickering world of particles where things appear and disappear, where certainty softens into probability. Each of these descriptions works beautifully on its own. If you want to understand how planets move, or how galaxies slowly drift across the dark, the theory of gravity guides you with quiet confidence. And if you want to understand atoms, light, or the tiny building blocks of matter, the quantum world reveals its patterns with astonishing precision. But there is a place where these two stories are forced to meet, and that place is a black hole. It is here, at the edge of one of these silent regions, that something unusual happens. Not an explosion, not a dramatic collapse that we can watch unfold, but something quieter and in some ways more unsettling. It is the realization that two perfectly successful descriptions of the universe cannot both be fully true at the same time, and yet they must be. You can think of it like listening to two pieces of music played together. Each one is beautiful on its own. Each one makes sense. But when they overlap, something feels off. A subtle dissonance. A tension that you cannot quite resolve, no matter how carefully you listen. Black holes are where that tension becomes impossible to ignore. And what makes them even more remarkable is that they are not hidden away in some unreachable corner of reality. They are not purely theoretical ideas, like imaginary shapes drawn on paper. They are real. They exist. We can see their influence. We can even, in a sense, take pictures of the shadows they cast against the glowing matter around them. They are out there, quietly shaping the universe. If you were to travel toward one, slowly, gently, with no rush, you would not immediately notice anything strange. Space would still look like space. Stars would still shine. But as you drift closer, something subtle begins to change. Not in the objects around you, but in the way time itself seems to move. Clocks far away would appear to tick faster. Light from distant stars would shift, stretching into softer, redder tones. And if someone were watching you from far away, they would see your movement slow, as if you were moving through thick, invisible syrup. And yet, from your own perspective, everything would feel normal, your heartbeat steady, your thoughts unchanged. 1 second still passing as 1 second always has. 2 different experiences of time, both real, both true. This is the kind of quiet strangeness that black holes bring into focus. They do not shout. They do not announce themselves with noise or chaos. Instead, they gently unravel the assumptions we carry without noticing. The idea that time flows the same everywhere. The idea that space is just an empty stage where events unfold. The idea that the universe at its deepest level is simple and consistent. Black holes suggest something else. They suggest that what we call space and time might not be as solid as they seem, that they might be more like patterns, emerging from something deeper, something we do not yet fully understand. And perhaps that is why black holes have become so important, not because they destroy things, but because they reveal things. They reveal the limits of our understanding. They reveal the places where our theories begin to stretch and strain, and in doing so, they offer us a rare opportunity, a chance to glimpse something just beyond the edge of what we currently know, a glimpse of what reality might truly be. So tonight, as we drift slowly through this story, we will not rush toward answers. We will move gently, step by step, following the quiet clues that black holes leave behind, from the bending of space to the soft glow of invisible radiation, to the strange idea that information itself might never truly disappear. And along the way you may begin to notice something, that the deeper we look into these dark places, the more they begin to illuminate everything else, and perhaps by the time your thoughts begin to soften and fade into sleep, the universe will feel just a little more mysterious, and a little more connected than it did before. As you continue to rest here for a while, letting your thoughts drift at their own quiet pace, it can be comforting to imagine that the universe, in all its vastness, is somehow understandable. That beneath the stars, beneath the slow turning of galaxies, there are patterns, steady, reliable, almost like the rhythm of breathing. For a long time that belief held strong. Physicists discovered that the universe seemed to follow 2 great sets of rules. Not simple rules, of course, but deeply elegant ones. Each set describing a different side of reality, like 2 languages telling the same story from different angles. One of these languages describes the large and the slow. It tells us how planets move, how stars are born and fade, how entire galaxies drift through space over billions of years. In this view, gravity is not something that pulls like an invisible rope. Instead, it is something softer, more subtle. Space itself bends, gently curving under the presence of mass, and everything simply follows those curves. You can picture it like placing a heavy object on a stretched fabric. The surface dips slightly, and anything nearby rolls toward it, not because it is being pulled directly, but because the surface beneath it is no longer flat. This way of seeing the universe is calm, continuous, smooth. Nothing jumps, nothing flickers, everything flows. And for the vast structures of the cosmos, this description works beautifully. But then there is another language, a very different one. This second way of describing the universe focuses on the small, the incredibly small, the world of atoms, of light, of particles that do not behave like tiny solid objects but more like possibilities, appearing, disappearing, interacting in ways that feel less like motion and more like patterns of chance. In this world, things are not always where you expect them to be. Events do not unfold with perfect certainty. Instead, there is a kind of gentle unpredictability, like watching the surface of water ripple in a light breeze. If the first description of the universe feels like a smooth fabric, this one feels more like a shimmering field, constantly in motion, even when nothing seems to be happening. And just like the first, this second language works remarkably well. It allows us to build technologies, to understand light, to describe the behaviour of matter at the smallest scales with astonishing accuracy. For decades, these two ways of seeing reality existed side by side, each one complete within its own domain, each one trusted. And for a while it seemed that perhaps they did not need to agree with each other at all, that maybe the universe was simply built this way. One set of rules for the very large, another for the very small. But then, black holes entered the story, because a black hole is not just large, and it is not just small, it is both. It is a place where enormous amounts of mass are compressed into an extremely small region, a place where the smooth curves of space become incredibly steep, and where the restless fluctuations of the quantum world cannot be ignored. It is here that the two languages are forced to speak at the same time, and when they do, something unexpected happens. They do not quite agree. You can imagine it like two maps of the same city, one drawn in careful flowing lines showing roads and rivers, the other drawn as a grid of tiny squares capturing every detail of each building. Each map is useful. Each one tells the truth in its own way, but when you try to place one directly on top of the other, they do not line up perfectly. The streets bend differently. The distances shift. The details refuse to match. And you are left with a quiet, persistent question. Which one is truly correct? Or is there something deeper that both are trying to describe in their own incomplete ways? Black holes bring that question into focus more clearly than anything else we know. Because at their edges, at the delicate boundary where the outside universe meets the interior, we encounter a strange situation. A place where, according to our best understanding, we should have full control over the physics. A place where our equations, both the smooth and the flickering, should apply cleanly. And yet, they do not fit together. This is not because the mathematics fails entirely. It is more subtle than that. Each theory continues to work in its own way. But when combined, they begin to suggest contradictions. Small at first, almost easy to overlook. But as you follow them further, they grow into something deeper, a tension that cannot simply be ignored. And this is what makes black holes so important, not because they are mysterious in the sense of being unknowable, but because they are precise. They ask clear questions. They point directly to the places where our understanding is incomplete. It is as if the universe, in these regions, is gently showing us the edges of our current ideas and inviting us to look beyond them. There is a phrase sometimes used in physics, a quiet, almost hopeful idea, that if you follow the clues carefully enough, if you continue to explore the places where your theories begin to strain, you may catch a glimpse of something deeper, something hidden beneath the surface of what you thought you understood. Black holes seem to offer exactly that kind of glimpse. They suggest that space and time, which we usually treat as the stage on which everything happens, might not be fundamental at all, that they could emerge from something more basic, something woven together from relationships rather than distances, from connections rather than locations, but that realization does not come all at once. It unfolds slowly. It begins with something much simpler, a boundary, a quiet, invisible surface in space surrounding the black hole, marking the point beyond which nothing can return. And as we move closer to that boundary, we begin to see just how strange the universe can become, even before we cross it. As your thoughts continue to drift, it can be soothing to step back, far back, into a time long before black holes had a name, a time when the night sky looked much the same as it does now, yet the ideas behind it were still forming, like faint outlines waiting to be filled in. In the late 18th century, long before telescopes could peer deep into distant galaxies, there were thinkers who began to wonder about gravity in a very simple, almost playful way. One of them was a quiet English clergyman named John Michel. Another was the French mathematician Pierre-Simon Laplace. Working independently, each of them have asked a question that seems almost childlike at first. What would happen if something became heavy enough? At the time, gravity was understood as a force that pulls things together. If you throw a stone upward, it rises for a moment, slows, and then falls back down. If you throw it harder, it goes higher, harder still, and higher again. There is, however, a special speed. A speed so great that if you could throw something that fast, it would never come back down. It would escape completely, leaving the pull of the earth behind forever. You can imagine it like tossing a ball. At first, it always returns. But if you could somehow throw it fast enough, it would keep going, rising and rising and rising, never turning back. This idea is known as escape velocity. Though the term itself sounds technical, the feeling behind it is simple. It is the difference between returning and leaving forever. Michel and Laplace wondered what would happen if you kept increasing the mass of an object, if you made it larger, heavier, more dense. The stronger the gravity, the faster something would need to move in order to escape. And then they imagined something extraordinary. What if there existed an object so massive that the required speed to escape it became faster than light itself? At the time, light was already known to have a finite speed, and nothing, it was believed, could move faster than that. So if the escape speed exceeded the speed of light, then not even light could leave. Such an object would be completely dark. Not because it absorbed light in the way a piece of charcoal does, but because light simply could not get away from it. It would shine, and yet no light would ever reach distant eyes. Laplace described these as dark stars, objects so large, so heavy, that they would be invisible, not by hiding, but by holding everything in. It is a remarkably beautiful idea, because it does not come from complicated mathematics or advanced instruments. It comes from following a simple thought to its natural conclusion, from asking gently, what if we keep going? And yet, at the time, these dark stars were only imagined. They were logical possibilities, not confirmed realities. There was no clear evidence that nature actually created such things. Still, the idea lingered, like a quiet suggestion, waiting. What makes this early vision so fascinating is that it captures something essential, even if it is not entirely correct by modern understanding. Michel and Laplace were thinking in terms of forces, of gravity pulling on objects, of speeds needed to escape. But the deeper truth, which would come much later, is that gravity is not simply a force in that sense. It is something more subtle. Still, the core intuition remains that there can exist regions of the universe where escape is no longer possible, where the idea of leaving loses its meaning. It is almost like standing at the edge of a waterfall where the flow becomes too strong to resist. No matter how hard you try to swim against it, the current carries you onward. Except here, the current is not water. It is space itself. These early thinkers did not yet have the language to describe that. They did not speak of curved space or warped time, but they sensed that something unusual might happen when gravity becomes extreme enough, and in that sense they were closer to the truth than they could have known. Their dark stars were not quite the black holes we understand today, but they were a beginning, a first step into a deeper question. Can gravity become so strong that it changes the very nature of reality? That question would remain, quietly waiting until the early 20th century. When a new way of understanding the universe began to take shape, a way that would transform gravity from a force into something far more surprising. something that would not just pull on objects, but reshape the stage on which everything exists, and, as that new understanding emerged, the idea of invisible stars would return, not as speculation this time, but as something written directly into the structure of space and time itself. As the idea of invisible stars slowly settled into the background of scientific thought, the universe itself remained for a time a rather steady place. Space was seen as a kind of silent stage, unchanging, unmoving, while objects danced upon it under the influence of forces like gravity. But in the early 20th century, something remarkable happened. The stage itself began to move. A young physicist named Albert Einstein looked at gravity in a completely different way. Instead of imagining it as a force pulling objects together across empty space, he asked a quieter, deeper question. What if gravity is not a pull at all? What if instead it is a change in the shape of space itself? It is a subtle shift in thinking, but one that changes everything. To picture this, you might imagine a wide, stretched surface, like a soft fabric pulled tight. If you place a heavy object in the centre, the fabric dips slightly. Not dramatically, just enough to create a gentle curve. Now, if you roll a smaller object across that surface, it will not travel in a straight line anymore. It will follow the curve, drifting toward the heavier object as if being pulled. But nothing is actually reaching out to grab it. It is simply moving along the shape of the surface beneath it. In Einstein's view, this is what gravity is. Mass does not pull on space. Mass shapes space, and everything else follows that shape. But there is another layer to this picture, one that is easy to miss at first, because Einstein did not just reshape space, he reshaped time as well. In his description, space and time are not separate things. They are woven together into a single structure, a kind of fabric that bends and stretches in response to matter and energy, so when something very massive is present, it does not just curve space, it also affects the flow of time. Time itself can slow down, or, from another perspective, appear to do so. This idea is not just philosophical, it has real, measurable consequences. Clocks placed in stronger gravitational fields tick more slowly compared to those farther away. The difference is usually tiny, almost imperceptible, but it is there, and when gravity becomes extreme, the effect becomes impossible to ignore. Around this time, not long after Einstein introduced this new way of seeing the universe, another physicist made a quiet but profound contribution. His name was Carl Schwarzschild. Working under difficult conditions during a time of war, Schwarzschild found an exact mathematical description of how space and time would behave around a perfectly simple, spherical mass. At first glance, this might not sound unusual. Physicists often find solutions to equations that describe different situations, but this one contained something unexpected. When Schwarzschild followed the equations all the way to their limits, he found that there exists a particular boundary, a radius around the mass, where the behavior of space and time becomes dramatically different. At this boundary, something curious happens. From the outside, it would appear as though time itself begins to slow down more and more, approaching stillness. Light trying to escape from this region would stretch, becoming fainter and redder, as if it were losing energy simply by trying to leave. And beyond this boundary, there is no return. Schwarzschild himself did not fully interpret this result as the black holes we understand today. At the time, the idea seemed too strange, too disconnected from physical reality. It was treated more as a mathematical curiosity than a prediction about the universe. But the solution remained, quietly waiting. What makes this moment in the story so fascinating is that black holes in this modern sense were not discovered. Through observation first, they were discovered through thought, through the careful exploration of what the equations of gravity were trying to say. It is as if the universe revealed something hidden, simply because someone followed the logic far enough, and what it revealed was not an object in the usual sense. It was a region, a distortion so complete that it forms a boundary, a place where the familiar rules of movement and escape no longer apply in the way we expect. If you imagine removing the star that created this distortion, leaving only the curve structure behind, what remains is still there. The geometry itself persists. The shape of space and time holds the imprint of what once was. This is one of the most unusual aspects of black holes. They are not made of something in the way a planet or a star is made of matter. Instead, they are defined by the way space and time are arranged, by the way the fabric of reality has been shaped. They are, in a sense, pure geometry, and yet they behave as if they are objects. They have mass. They influence their surroundings. They can even collide and merge, sending ripples through space itself. It is a strange combination, something that is both there and not there in the way we expect. As this understanding slowly took hold, physicists began to realize that these solutions were not just mathematical artifacts. They could describe real things, objects that form when massive stars collapse under their own gravity, compressing themselves beyond the point where any known force can stop them. And so, the old idea of dark stars returned. But now it was no longer based on simple intuition about escape speeds. It was rooted in the very structure of space and time. Gravity was no longer just a force, it had become a geometry, and black holes were no longer just hypothetical curiosities. They were inevitable consequences of the way the universe is built. As we move closer to these regions, following the curves of space itself, we begin to encounter the boundary that Schwarzschild's work hinted at. A surface that is not solid, not visible, and yet deeply real. A surface where time begins to drift, and where the familiar rules of the universe start to gently come undone. As the idea of black holes slowly took shape, there was one feature that began to stand out more than any other. Not the centre, not the collapse, not even the immense gravity itself, but a boundary. A surface that is not solid, not visible, and yet deeply meaningful. This boundary is known as the event horizon. It is often described as the point of no return. But even that phrase can feel a little too dramatic, a little too sharp. Because in truth, nothing special seems to happen at that exact location, at least not in the way you might expect. There is no wall, no sudden jolt, no flash of light. If you were drifting gently through space, approaching a black hole, you would not see a glowing line or a dark edge marking where the horizon begins. There would be no signpost telling you that you're about to cross into something fundamentally different, and yet something profound is there. To understand it, it helps to shift the way we think about movement. Normally when we move, we imagine choosing a direction. Forward, backward, left, right. We imagine space as something open, something that allows us to go wherever we wish, as long as we have enough energy. But near a black hole, this idea begins to change. A useful way to picture it is to imagine standing in a river. At first, the current is gentle. You can walk upstream if you wish, or drift downstream. You have freedom of movement. As you move further into the river, the current grows stronger. It becomes harder to resist. You can still move against it, but it takes more effort. And then, eventually, you reach a point where the current becomes so strong that no matter how hard you try, you cannot swim back. You are still moving. You're still choosing your path in a sense. But all possible paths lead in the same direction. That is what the event horizon is like. It is not a place where something pulls you in suddenly. It is a place where the structure of space and time itself has been shaped in such a way that every possible future leads inward. Even light, which normally travels as fast as anything can, finds that all of its possible paths curve back toward the black hole. It is not that light slows down, it is that the direction of away no longer exists. This is a subtle but important distinction. From the outside, it may look as though something is being trapped, as though there is a force holding things back. But from within the geometry of space-time, it is more accurate to say that escape is no longer a valid path. The horizon marks the point where this change becomes complete, and yet, from the perspective of someone falling inward, crossing this boundary would feel ordinary. If the black hole is large enough, there would be no sudden stretching, no immediate tearing apart. You would drift across the horizon without noticing anything special at that exact moment. Your clock would tick normally. Your thoughts would continue. Your experience of time would remain unchanged. But for someone watching from far away, the story looks very different. They would see you slow down as you approach the horizon. Not because you're choosing to slow down, but because time itself, as seen from their perspective, is passing more slowly for you. The closer you get, the more pronounced this effect becomes. Your movements appear to stretch out. Your signals take longer to arrive. Your image begins to fade, shifting toward longer, softer wavelengths of light. And eventually, from their point of view, you seem to hover at the edge, never quite crossing. It is as if time pauses at the horizon, but only from the outside. From your own perspective, nothing pauses at all. This is one of the quiet paradoxes that black holes reveal. Two observers, each with their own perfectly valid experience, describing the same event in two completely different ways. Neither is wrong, but they do not match. And this is where something deeper begins to emerge. Because the event horizon is not just a boundary in space, it is a boundary in information. For an observer outside, anything that crosses the horizon becomes inaccessible, not destroyed, not erased, but hidden beyond reach. The information about what falls in seems to fade away, carried with the object as it disappears from view. And yet physics tells us that information should not simply vanish. It should remain, in some form, encoded in the universe. This tension, this quiet disagreement between what we expect and what we observe, begins right here at the horizon, not at the center, not in some unreachable singularity, but at a boundary we can describe, a boundary we believe we understand. And that is what makes it so important, because it suggests that the mystery of black holes is not hidden in some distant, unknowable place. It is present at the very edge, where our current theories should be strongest. The horizon becomes more than just a surface. It becomes a question, a place where the universe gently asks us to reconsider what we mean by space, by time, and by the very idea of what it means for something to exist, to move, or to be lost. As we continue to drift closer to this boundary in our understanding, we begin to notice something even stranger. That beyond the horizon lies not just a region of no return, but a place where the concept of where itself begins to dissolve, and where the future takes on a meaning we have not yet fully grasped. If you remain for a while at the edge of this quiet boundary, letting the idea of the event horizon settle gently in your mind, something even more subtle begins to reveal itself. It is not the darkness, not the gravity, but time. We often think of time as something steady, something that flows the same way everywhere, like a calm river moving at a constant pace. Seconds pass, one after another, in a rhythm so familiar that we rarely question it. But near a black hole, that rhythm begins to change. Not suddenly, not in a way that startles you, but gradually. almost imperceptibly at first. Imagine again that you're drifting through space, moving slowly toward the black hole. You carry with you a simple clock. It ticks in a steady, reassuring way. 1 second follows another, just as it always has. From your perspective, nothing feels unusual, but far away, someone is watching you. They too have a clock, and when they look toward you, they notice something strange. Your clock does not seem to match theirs anymore. At first, the difference is tiny, almost impossible to notice. But as you move closer to the black hole, the gap begins to grow. Your clock appears to tick more, slowly. Each second stretches just a little longer, and as you approach the horizon, this effect becomes more and more pronounced. Your movements seem to slow, your signals take longer to reach the observer, and the light you send back begins to soften and fade. Eventually, from their perspective, it seems as though you are almost frozen in time, hovering at the edge, never quite crossing. And yet, from your own perspective, nothing like that is happening at all. Your clock continues its steady rhythm. Your thoughts unfold normally. You do not feel slowed, you do not feel stretched. Time, for you, continues exactly as it always has, one moment gently following the next. This is one of the most beautiful and unsettling ideas in modern physics. Time does not flow the same for everyone. It is not a universal background ticking away independently of everything else. Instead, it is woven into the structure of the universe, shaped by gravity, influenced by motion, and experienced differently depending on where you are and how you move. Near a black hole, this difference becomes impossible to ignore. It is not that time slows down in a simple sense. It is that time becomes relative, dependent on perspective. Two observers can disagree about how much time has passed, and both can be completely correct. You might think of it like listening to music from different rooms in a house. In one room, the sound is clear and direct. In another, it is softer, slightly delayed, perhaps echoing faintly off the walls. The same melody is playing, but the experience is not identical. Time, near a black hole, is a little like that. It is the same underlying reality, but shaped by where you stand. And this leads to a curious consequence. From the perspective of the distant observer, you never quite cross the horizon. Your image fades, your signals weaken, and you seem to linger at the edge indefinitely. But from your own perspective, you pass through without hesitation. There is no pause, no hesitation, no infinite delay, just a quiet continuation forward. This creates a kind of gentle contradiction. Did you cross the horizon? From one point of view, yes. From another, not yet. And both perspectives are valid within the framework of physics. This is not a mistake or a failure of the theory. It is a reflection of how deeply intertwined space and time have become in this description of the universe. It also begins to hint at something deeper. Because if time can stretch, if it can slow, if it can appear to pause from one perspective while continuing normally from another, then perhaps time is not as fundamental as we once believed. Perhaps it is not a fixed background, but something that emerges from the relationships between observers, between motion, between gravity and geometry. Near a black hole, these relationships become extreme, and in those extremes, hidden patterns begin to surface. There is also a quiet emotional quality to this idea. The notion that from far away, you would seem to linger forever at the edge, that your final moments, as seen by the distant observer, would stretch out endlessly, never quite completing. While for you, time continues onward, leading you deeper into a region from which no signal can return. It is as if two different stories are being told at once, one that fades into stillness, and one that continues into the unknown. Black holes invite us to hold both of these stories in mind at the same time. Not to resolve them immediately, not to force them into a single picture, but to sit with the tension between them. To accept that reality, at its deepest level, may not always align with our everyday intuition. And as we continue this quiet journey, moving gently closer to the center of these strange regions, we begin to encounter an idea that is even more surprising. Because beyond the horizon, where all paths lead inward, there lies not just a place in space, but a moment in time, a final moment, one that cannot be avoided. If you let your thoughts drift just a little further, beyond the gentle slowing of time, beyond the quiet boundary of the event horizon, you begin to approach an idea that feels almost impossible to hold. Not because it is complicated, but because it asks you to let go of something very familiar, the idea that every moment is followed by another. We live our lives with a simple expectation that time continues, that after this second comes the next, that the future, whatever it may hold, is always waiting somewhere ahead. Even when we cannot see it, we trust that it exists. But inside a black hole, according to our best understanding, this expectation begins to break. At the heart of a black hole lies something called a singularity. The word itself sounds sharp, almost abrupt, but its meaning is more subtle than it first appears. It is often described as a point of infinite density, a place where matter is compressed without limit. And while that image is not entirely wrong, it can be misleading, because the singularity is not simply a place. It is not like a hidden core that you could, in principle, move around or avoid. Instead, it is something closer to a moment, a final moment. To understand this, it helps to return to the idea that space and time are woven together. Near a black hole, this woven structure becomes so distorted that the roles of space and time begin to shift in a quiet but profound way. Outside the black hole, you can choose your direction in space. You can move left or right, forward or backward, and time flows onward, carrying you with it whether you choose to move or not. But inside the event horizon, this freedom changes. All possible directions through space begin to point inward, toward the singularity. No matter which way you turn, no matter how gently you try to drift, every path leads deeper. It is not that something is pulling you toward the center. It is that the structure of reality itself has been arranged so that toward the center is no longer just a direction in space. It is the direction of time. Just as outside the black hole, you cannot choose to stop time from moving forward, inside the black hole, you cannot choose to avoid the singularity. It is not ahead of you in space. It is ahead of you in time. This is a very different way of thinking. Imagine waking up in the morning and knowing that no matter what choices you make, no matter where you walk or what path you take, you will inevitably arrive at a particular moment later in the day. Not because something is guiding you there, but because it is simply part of the structure of your day. Inside a black hole, the singularity is like that, an unavoidable future, a point not in space but in time where all paths converge. Physicists sometimes describe this using diagrams that map out how space and time behave in extreme conditions. In these maps, the singularity does not appear as a location you can point to. It appears as a boundary in the future, a place where the usual rules of physics can no longer describe what happens. And this is where our understanding begins to fade, because as you approach the singularity, the curvature of space and time grows without limit. The gentle bending we imagined earlier becomes sharper, more extreme, until the concepts we rely on, distance, duration, even causality, begin to lose their meaning. Our current theories can guide us part of the way, but not all the way. It is as if the map becomes increasingly detailed as you move closer, and then suddenly it ends, not because there is nothing there, but because we do not yet know how to describe it. For a long time, this was thought to be the central mystery of black holes, the unreachable core hidden beyond the horizon, where physics itself seems to fall silent, and in a sense, it still is. But something even more surprising would emerge later, a realization that the deepest questions about black holes might not lie at this distant hidden endpoint, but at the boundary we can observe, the horizon itself. Still, the singularity remains an important part of the story, not because we fully understand it, but because of what it represents. It represents the limits of our current knowledge. It marks the place where our descriptions of the universe, so successful elsewhere, begin to break down, and perhaps most intriguingly, it connects to another mystery. Because there is another singularity we often speak of, not at the end of time, but at the beginning, the moment we call the Big Bang. A time when the universe itself was compressed into an extremely hot, dense state. A moment beyond which our current understanding cannot easily reach. It is tempting to wonder whether these two ideas are related. The singularity inside a black hole, where time seems to end, and the singularity at the beginning of the universe, where time seems to begin. Are they reflections of the same deeper structure? Two edges of a reality we do not yet fully see? For now, these questions remain open. But as we continue this gentle journey, we will begin to notice that black holes do something unexpected. They do not simply hide answers, they illuminate them. And in a surprising twist, the next clue does not come from the depths of the singularity, but from the quiet surface of the horizon itself, where something that should have remained dark begins to glow. As you linger gently with the idea of a place where time bends and paths converge, it might seem natural to imagine a black hole as something final, a silent region where everything disappears, where nothing returns, and where darkness simply remains, unchanged. For a long time, that is exactly how black holes were understood. They were seen as perfect absorbers, endpoints, cosmic wells from which no light, no signal, no information could ever escape. Once something crossed the horizon, it was gone from the rest of the universe, forever hidden behind that quiet boundary. It is a simple picture, a very clean one, and for a while, it seemed complete. But then, in the 1970s, a young physicist named Stephen Hawking began to look more closely at what happens near the edge of a black hole. Not deep inside, not at the unreachable singularity, but right at the horizon itself. And what he found was something unexpected, something that changed the story entirely. To understand this, it helps to soften our idea of empty space. We often think of empty space as truly empty, a kind of quiet void where nothing happens. But in the language of modern physics, even the emptiest region is never completely still. If you could somehow zoom in, far beyond what any microscope could ever achieve, you might begin to notice something subtle. Tiny fluctuations, brief appearances and disappearances, like faint ripples moving across a perfectly calm lake. These are not particles in the usual sense, not stable objects travelling through space. They are more like momentary flickers, pairs of tiny disturbances that appear together, exist for a brief instant, and then fade away again. You can imagine them as brief whispers in the fabric of reality. They arise, they meet, and they vanish. Everywhere, all the time, even in the emptiest space you can imagine. Now, normally these fleeting pairs do not leave any lasting trace. They appear and disappear so quickly that the universe on larger scales remains calm and unchanged. But near a black hole, something different can happen. At the edge of the event horizon, Where space and time are already stretched into unusual shapes, these tiny pairs can become separated. One of them may drift just slightly inward, crossing the horizon. The other may drift outward, and once they are separated in this way, they cannot reunite. The one that moves outward stays. It becomes real, not because it was created from nothing, but because it is no longer able to return to the quiet balance it once had with its partner. And as it escapes, it carries energy away from the black hole. This is what we now call Hawking radiation, a very soft glow, not bright, not dramatic, not something you would easily notice, but a steady, gentle release of energy into the surrounding universe. It is as if the black hole, which we once thought of as completely dark, is actually giving off a faint warmth, a whisper of light. And this changes everything. Because if a black hole can emit energy, even in this quiet and subtle way, then it cannot remain unchanged forever. Slowly, over immense stretches of time, it must lose mass. It must shrink. The process is unimaginably slow for large black holes. So slow that on human timescales, or even the timescales of stars and galaxies, it appears almost frozen. But given enough time, far longer than the current age of the universe, it would continue, gradually, patiently, until, eventually, the black hole would fade away. This idea is both surprising and strangely comforting, because it suggests that black holes are not eternal prisons. They are not final endpoints. They are part of a cycle. Things fall in, and in a very different form, something comes back out. Not the same shapes, not the same structures, but something that carries traces of what once was, like the faint scent of smoke long after a fire has gone out, or the warmth that lingers in a room after a candle has been extinguished. And yet, this gentle glow raises a quiet question. If black holes slowly release energy back into the universe, what exactly are they releasing? Because what falls into a black hole is not just mass, it is structure, it is information. The arrangement of particles, the patterns that define objects, the details that make something what it is. If all of that disappears behind the horizon, and what returns is only a soft, featureless glow, then something seems to be missing. It is as if a detailed story were burned into ash, and all that remained was a uniform cloud of smoke. Where did the details go? Were they lost? Or are they hidden somehow within that faint radiation, waiting to be understood? This question would grow into one of the deepest puzzles in modern physics. But for now, it's enough to sit with the quiet realization that black holes are not as simple as they once seemed. They do not merely absorb, they also emit. They do not simply end stories, they transform them. And as we follow this gentle trail of light drifting outward from the horizon, we begin to see that even the emptiest space is full of quiet activity, and that even the darkest objects in the universe may carry within them a soft and persistent glow. If you stay with this image for a moment, the faint glow of something once thought completely dark, you may begin to feel that space itself is not as empty as it seems. It is easy to imagine the universe as a vast, silent expanse, a place where stars drift far apart and where the spaces between them are simply nothing. But as we gently look closer, that nothing begins to feel more like a quiet kind of activity. Not loud, not chaotic, but never truly still. You might imagine sitting beside a calm lake in the early evening. At first glance, the surface appears perfectly smooth, but if you watch closely, you begin to notice tiny ripples forming and fading, barely disturbing the surface. They appear, they soften, they disappear. And then, without warning, another set forms somewhere else. This is a helpful way to picture what physicists mean when they say that empty space is not truly empty. At the smallest scales we can imagine, space is filled with tiny fleeting events, brief appearances of energy that come in pairs, not solid objects, not lasting structures, but temporary patterns that exist just long enough to be noticed. If you could look closely enough, they arise together, and they vanish together. Like two dancers stepping briefly into the light before slipping quietly away. In most places, these pairs remain perfectly balanced. They meet, they cancel, and nothing changes. The universe remains calm on larger scales, even though these tiny dances are happening everywhere. But near a black hole, the stage itself is different. The flow of space and time has been stretched and tilted in such a way that these pairs can be pulled apart. Imagine two dancers holding hands at the edge of a slowly moving current. Under normal conditions, they would move together, step for step, and then leave the stage as one. But if the current becomes strong enough, it can separate them. One is carried inward, the other is pushed outward. And once that connection is broken, the balance is lost. The dancer who moves outward cannot simply return. The pairing is incomplete. And so, what was once a fleeting event becomes something more lasting, something real. This is the heart of the process behind Hawking radiation. The black hole does not create something from nothing. Instead, it gently disrupts what is already happening in the fabric of space. It allows one half of these fleeting pairs to escape, and in doing so, it slowly gives away a tiny amount of its own energy. You can think of it like a very slow leak. Not a dramatic burst, not a sudden release, but a steady, almost imperceptible flow. A black hole, over vast stretches of time, gradually loses a little of itself, one small whisper at a time. Each escaping particle carries away a trace of energy, and as this process continues, the black hole becomes slightly smaller, then smaller still. The change is so slow that it would be impossible to notice over any ordinary span of time. Even over the entire history of human civilization, the difference would be negligible. But over timescales far beyond our everyday experience, times longer than the lifetimes of stars, longer than the current age of the universe itself, the effect becomes meaningful. The black hole fades. It does not disappear all at once. It diminishes, like a glowing ember slowly cooling in the dark. This gradual shrinking leads to a curious thought. If black holes can lose energy, then they must have a kind of temperature. Not in the way we think of a warm object in our hands, but in a more subtle sense. A measure of how they exchange energy with their surroundings. It is a quiet reminder that black holes, for all their strangeness, are not entirely separate from the rest of physics. They follow rules. They participate in the same gentle exchange of energy that governs everything else. And yet, there is something different here. Because what is being released does not seem to carry any obvious detail about what fell in. If you imagine throwing different objects into a black hole, a book, a stone, a beam of light, the radiation that eventually emerges does not appear to distinguish between them. It is as if all the rich detail, all the structure, all the information about those objects has been smoothed away. The radiation looks simple, uniform, featureless, and this brings us to a quiet but persistent tension. Because in physics, there is a deeply held idea that information is never truly lost. That even if something is broken apart, scattered, or transformed, the underlying details remain encoded in some way. Like a melody that can be reconstructed if you gather all the echoes. But here, it seems as though the melody has faded into a single, uniform tone, and we are left wondering, is the information truly gone? Or is it still there, hidden within the radiation in a way we do not yet understand? This question does not shout. It does not demand immediate attention. It lingers, softly, like a thought that returns again and again, each time a little clearer, a little harder to ignore. And as we continue to follow this gentle trail, this slow release of energy, this quiet dance of particles, we begin to see that the mystery of black holes is not just about what falls in, it is about what comes out, about whether the universe remembers or forgets. If you follow this quiet process a little further, the slow release of energy, the faint glow drifting outward, you begin to sense something almost unexpected, a kind of return. For a long time, black holes were imagined as endings, final destinations where matter and light would gather, never to be seen again, a place where stories simply stopped. But now the picture feels different, not an ending, but a transformation. You might imagine a small fire burning in the distance. At first it is bright, full of structure, flames rising and falling, shape shifting in constant motion. If you place something into that fire, its form disappears. The details are lost to the eye, the structure dissolves, and yet something remains. Warmth spreads outward. Light flickers into the surrounding space. Smoke rises, carrying with it traces of what once was. The original object is no longer visible in its original form, but it has not simply vanished. It has changed, become part of something more diffuse, more subtle. A black hole, in its own quiet way, behaves similarly. When something falls into it, the structure we recognize seems to disappear. The details are hidden beyond the horizon. From the outside, it appears as though the story has ended. But over time, over vast, almost unimaginable stretches of time, the black hole begins to give something back. Not in the same shape, not in the same arrangement, but in a softer, more dispersed form. A steady whisper of radiation, a gradual return of energy to the universe. It is not dramatic. There is no sudden release, no final burst that announces the end. Instead, it is a slow fading, like a glowing ember cooling in the dark. At first, the black hole remains large, almost unchanged. The radiation it emits is so faint that it is nearly impossible to detect. The universe around it continues as usual, stars forming and fading, galaxies drifting quietly through space. But as time stretches onward, far beyond the lifetimes of stars, far beyond the current age of the universe, the process continues. The black hole shrinks, little by little. Its glow becomes slightly more pronounced as it loses mass, as though the fading ember briefly brightens before it cools completely. And eventually, after an almost inconceivable amount of time, the black hole disappears, not with a dramatic collapse, but with a final gentle release of its remaining energy, a soft ending. This idea reshapes the way we think about black holes. They are no longer eternal. They are not permanent features of the universe. They are temporary, long-lived certainly, lasting far longer than stars, far longer than galaxies in many cases, but not forever. Everything that falls in is, in some sense, returned, and yet this return is not simple, because when we look at the radiation that comes back, it does not seem to carry the same richness as what went in. If you imagine throwing a book into a fire, the smoke that rises does not contain readable pages. The warmth does not preserve the words. The structure, the meaning, appears to be gone. In the case of a black hole, the radiation it emits appears similarly uniform. It does not seem to distinguish between what fell in. Whether it was a star, a cloud of gas, or something more complex, the outgoing radiation looks the same. And this raises a quiet but persistent question. If everything is returned, what exactly is being returned? Is it just energy, stripped of all detail? Or is there something more subtle hidden within it? Something that still carries the imprint of the past, even if we cannot easily see it? Because in physics, there is a deeply held principle that information is not destroyed, that the details of what happens, the arrangement of particles, the structure of objects, must remain encoded in some way, even if they are scattered or transformed. It is a principle that is held true in every situation we have studied. Burn a book, and in principle, if you could gather every particle, every bit of light, every trace of heat, you could reconstruct the original text. The information is not lost. It is simply dispersed. But black holes seem to challenge this idea, because here the return appears incomplete. The outgoing radiation seems too simple to contain the full story of what fell in. And so we are left with a quiet tension. On one hand, black holes slowly give back what they have taken. On the other, what they return does not seem to match what was lost. It is as if the universe is speaking in a softer voice, hinting at something deeper, something not yet fully understood. And this tension does not resolve easily. It lingers, like a question that continues to echo even after the sound has faded. Because if information truly disappears inside a black hole, then something fundamental about our understanding of the universe must change. But if it does not disappear, if it is somehow preserved, hidden within that faint radiation, then there must be a deeper mechanism at work, a way in which the universe keeps track of its own history, even in the most extreme conditions. This question, simple in form yet profound in its implications, becomes one of the central puzzles in modern physics, not a distant mystery hidden at the center of a black hole, but a question that arises from what we can observe, from the gentle glow, from the slow return. And as we move forward, following this thread, we begin to see that the true mystery of black holes is not just about what they take in, but about whether the universe ever truly forgets. As the idea of a black hole slowly fading back into the universe settles in your mind, a quieter question begins to take shape. Not about what happens to matter, not even about energy, but about something more delicate: information. It is a word we use often, almost casually. The information in a book, the information in a photograph, the information carried by a message. It feels intangible, almost weightless. And yet, in physics, information has a very specific meaning. It is the detailed description of how something is arranged, the exact pattern of atoms in a page of text, the precise structure of a molecule, the unique configuration that makes one object different from another. If you change the arrangement, you change the information. And one of the most quietly powerful ideas in modern physics is this: information is never truly lost. It may be scrambled, it may be spread out, it may become so dispersed that it is nearly impossible to recover, but in principle it remains. You can imagine a library filled with books, each book containing stories, ideas, patterns of words arranged in meaningful ways. Now imagine that library catches fire, the shelves collapse, the pages burn, the structure disappears in a cloud of ash, heat, and light. To any observer, it looks like everything has been destroyed. The stories are gone, the words are gone, the information has vanished. But if you could somehow gather every particle released by that fire, every wisp of smoke, every bit of heat, every photon of light, and if you could analyze them with perfect precision, you would find that the information is still there, hidden, scattered, encoded in an incredibly complex way. The original books could, in principle, be reconstructed, not easily, not practically, but fundamentally the information has not been erased. It has only changed form. This idea has been tested again and again in different areas of physics, and it has always held true. It is woven deeply into the way we understand the universe. And this is where black holes begin to trouble that understanding. Because if you take that same library and instead of burning it, you drop it into a black hole, something different seems to happen. From the outside, you would watch the books approach the horizon. their images would slow, stretch, and fade, and eventually they would disappear from view, gone behind the boundary, and over time the black hole would emit its faint radiation, slowly returning energy to the universe. But here is the problem. That radiation appears to be simple, uniform. It does not seem to carry the intricate details that made each book unique. It is as if, instead of a complex cloud of ash containing hidden information, the universe produces a smooth, featureless mist. And if that is truly the case, then something extraordinary has happened. Because the information about those books, the exact arrangement of their pages, the precise order of their words, would be gone, not hidden, not scrambled, but erased. And that is something physics does not easily allow. This creates a quiet but profound conflict. On one side, we have the principles of quantum physics, which tell us that information must be preserved, that the universe keeps track of its details, no matter how deeply they are hidden. On the other side, we have the behavior of black holes, which seems to suggest that information can simply disappear. Both ideas are well supported. Both have been tested in their own domains. And yet, when brought together, they do not quite fit. It is like having two maps of the same landscape, each carefully drawn, each accurate in its own way, but when placed together, revealing a mismatch that cannot be ignored. This is the beginning of what is known as the black hole information paradox. But even that word, paradox, can feel a little too sharp. It suggests something dramatic, something broken. In reality, it is quieter than that. It is more like a question that refuses to settle, a tension that lingers. Because if information can be destroyed, then the foundation of quantum physics must be rethought. And if it cannot be destroyed, then our understanding of black holes must be incomplete. Either way, something deeper is waiting beneath the surface. And what makes this question especially intriguing is that it does not arise from some distant, unreachable place. It does not depend on the unknowable conditions at the center of a black hole. It emerges from the horizon, from a region we believe we understand, from physics we trust. And that is what gives it its quiet power. Because it suggests that the mystery is not hidden in some faraway corner of the universe. It is right at the edge, in a place where our best ideas should work, but do not quite align. As you sit with this thought, letting it settle gently, you may begin to feel that black holes are not just strange objects. They are questions, carefully posed, waiting to be answered. And the answer, whatever it may be, will not only tell us about black holes, but about the deeper nature of reality itself. Time equals, quote, 3 seconds, quote, / greater than. If you remain with this idea for a little while, the image of a library that should not truly be lost, you may begin to notice something unusual. The question does not go away. It does not resolve itself into a simple answer. It does not fade like a passing thought. Instead, it lingers, softly, persistently, like a quiet echo that keeps returning. Because what we are facing here is not just a curious detail about black holes. It is a question about the rules of the universe, and unlike many mysteries in science, this one is not vague or distant. It is not about something we cannot define or measure. It is in a sense very precise. We can describe the situation clearly. We can follow the logic step by step. And that is what makes it so compelling. On one side, there is a deeply trusted principle from quantum physics. It tells us that if we know the complete state of a system at one moment, then, in principle, we can trace its evolution forward or backward in time. The details may become incredibly complex, spread out, or difficult to reconstruct, but they are not destroyed. It is like watching a drop of ink fall into a glass of water. At first, the ink forms a clear, visible shape. Then it begins to swirl, stretching into delicate patterns, eventually spreading throughout the entire glass. After a while, the water looks uniformly coloured. The original drop seems to have disappeared, but if you had perfect knowledge of every tiny movement within the water, every swirl, every current, you could, in principle, reverse the process. You could gather the ink back into its original shape. The information is still there, it has simply been dispersed. This is the expectation that quantum physics carries with it. Now, on the other side, we have black holes, objects that, according to our current understanding, absorb information and then emit radiation that appears to be simple, lacking the detailed structure of what fell in. If that radiation truly contains no trace of the original information, then the story cannot be reversed. The details would be gone in a fundamental way, not hidden, not scrambled, but erased. And this is where the tension becomes unavoidable, because both of these ideas are supported by strong reasoning. Quantum theory has been tested with extraordinary precision. Its predictions match experiments in ways that are almost astonishing in their accuracy. And the description of black holes, based on the bending of space and time, has also been confirmed through observation. We see their effects. We detect the ripples they create when they merge. We have even captured images of their shadows. So we are left with a quiet dilemma. Two well-tested ideas, both successful, both reliable, and yet when brought together, they seem to disagree. It is tempting to think that one of them must simply be wrong. But the situation feels more subtle than that. It is not as though either theory fails completely. They each continue to work in the domains where they have always been trusted. The tension only appears when we try to apply them together in the extreme conditions near a black hole. This suggests something different, not that one theory is incorrect, but that both are incomplete, that there is a deeper description of reality, one that we have not yet fully discovered, that would allow these two pictures to fit together without contradiction. This is why the question of black holes has become so important, not because it is unsolved, but because it is solvable. In a sense, it is a well-defined puzzle, a problem that can be approached, analysed, explored with careful thought. It is not like asking what happened before the universe began, where even the question itself becomes difficult to define. Here, the question is clear, and that clarity gives it a special kind of weight. It invites us to look more closely, to follow the clues, and one of the most interesting aspects of this puzzle is where the clues seem to point. At first, it might seem natural to look toward the singularity, the deep interior of the black hole, where our current theories break down. But over time, physicists began to realize that the key to the paradox may not lie there at all. Instead, it may be found at the boundary, at the horizon, the place we thought we understood. This is a subtle shift, but an important one. It suggests that the mystery is not hidden in the most extreme, unreachable regions of space. It is present at the edge, in the behavior of the radiation, in the way information might be encoded rather than destroyed. It is as if the answer is not buried deep inside the black hole, but written quietly along its surface. And this brings us to a new way of thinking, a possibility that the radiation is not as simple as it appears, that within its soft uniform glow there may be an intricate pattern, a pattern so subtle, so delicately arranged, that it escapes easy detection, like a whisper hidden within noise, or a message woven into a fabric that looks, at first glance, perfectly smooth. If this is true, then the information is not lost, it is preserved, but in a form that requires a deeper understanding to decode. And this idea begins to open a new path, a way forward that does not require abandoning the principles of quantum physics, nor rejecting our understanding of black holes. Instead, it suggests that we need to rethink how information is stored, how it is spread, how it is encoded in the universe. And as we follow that path, we begin to encounter an idea that is both surprising and strangely elegant. That the surface of a black hole, the very boundary we've been circling, may hold more information than we ever expected. That it may, in some sense, contain the story of everything that has fallen in, and perhaps, in a much broader way, the story of reality itself. If you stay with the question just a little longer, the quiet uncertainty of whether the universe forgets or remembers, you may begin to notice a subtle shift. What once felt like a contradiction begins to feel more like a hint. Because the radiation drifting away from a black hole, that faint and seemingly featureless glow, may not be as simple as it first appears. At a distance it looks uniform, soft, almost random, like a gentle hiss in the background of a quiet room. But sometimes what appears as noise at first can carry something deeper. You might imagine listening to a radio late at night, turning the dial slowly. At certain frequencies, all you hear is static, a soft, shapeless sound without clear structure. But hidden within that static, if you listen carefully enough, there can be signals, patterns, voices that are difficult to distinguish, but not entirely absent. The information is there, it is simply buried beneath layers of complexity. Something similar may be happening with the radiation from a black hole. When we first look at it, it seems to carry no detailed memory of what has fallen in. It does not distinguish between different objects. It does not reflect the intricate structures that once existed beyond the horizon. But this first impression may be misleading, because the way information is stored in the universe is not always obvious. It is not always written in clear, readable patterns. Sometimes it is woven into subtle correlations, tiny relationships between particles, faint connections between events that, taken individually, appear random, but together form something meaningful. Imagine a long string of seemingly random numbers. At first glance they appear chaotic, without order. But if you knew the rule that generated them, you could reconstruct the entire sequence from a small part. The structure is hidden, not absent. In the case of black holes, some physicists have begun to suspect that the radiation may carry information in a similarly subtle way, not as clear, distinct pieces, but as patterns distributed across the entire stream. Like a message that has been broken apart and spread across many fragments, each one incomplete on its own, but together forming a coherent whole. This idea begins to ease the tension, because it suggests that information is not destroyed. It is transformed, encoded in a form that is far more complex than we initially expected. Instead of a simple, uniform glow, the radiation becomes something richer, something structured in ways that are difficult to detect but not impossible. You might think again of the fire. When a book burns, the pages disappear, the words vanish from sight. But the smoke, the heat, the light, all carry subtle traces of what was there before. Not in a way that is easy to read, but in a way that is still, in principle, complete. The challenge is not that the information is gone. The challenge is that it has been scattered into a form that is incredibly delicate, incredibly intricate. And this is where a new kind of understanding begins to emerge. An understanding that information does not need to remain localized. It does not need to stay in one place or in one recognizable form. It can be spread out, distributed, shared across a system in ways that make it resilient, even when parts of that system seem to disappear. In this view, the black hole is not erasing information, it is reshaping it, stretching it across the boundary, encoding it into the radiation that slowly escapes. And as this idea develops, it begins to connect with something even more surprising. Because if information can be stored in such subtle, distributed ways, then perhaps the surface of a black hole, the horizon itself, plays a more important role than we once imagined. Perhaps it is not just a boundary. Perhaps it is a kind of record, a place where information is written, stored, and slowly released. This leads to a quiet but profound shift in perspective. Instead of thinking of the black hole as a deep container holding everything inside, we begin to think of it as something more like a surface, a boundary that carries information, a kind of memory. And if that is true, then the interior of the black hole, the space we imagine beyond the horizon, may not be the primary place where information resides. It may be in some sense secondary, a reflection of what is encoded at the boundary. This is a subtle idea, and it does not demand immediate clarity. It is enough for now to let the image settle, a black hole, not as a silent absorber, but as something that remembers, not in a way that is obvious or easily read, but in a way that is woven into the faint glow that surrounds it, a memory carried outward, slowly, patiently, across vast stretches of time. And as we follow this gentle thread, we begin to see that the horizon, the quiet edge we have been circling, may hold more than just a boundary between inside and outside. It may hold the key to understanding how the universe keeps track of itself, how it preserves its own story, and perhaps how the very fabric of reality is built, not from things, but from the information they carry. If you let this idea settle, the possibility that a black hole remembers, not through obvious structure, but through something subtle and distributed, you may begin to notice a quiet shift in perspective. The focus moves, not toward the center, but toward the surface. That thin, invisible boundary we have been circling, the event horizon, begins to feel less like an edge and more like something important in its own right. A place where something is happening. A place where information might be stored. This idea did not emerge all at once. It grew slowly from careful thought, from small clues gathered over time. And one of the most important of those clues came from a physicist named Jacob Bekenstein. He was thinking about black holes in a slightly different way. Instead of asking what falls into them, he asked a quieter question. How much information can they hold? It is not an obvious question at first. We do not usually think of objects in terms of how much information they contain. But in physics, information is closely tied to something called disorder, the number of different ways a system can be arranged while still appearing the same from the outside. A simple object has fewer possible arrangements. A complex object has many. And this complexity can be thought of as a kind of hidden richness, a measure of how much information is contained within. Bekenstein realized that if black holes truly absorb information, then they must have a way of storing it. Otherwise, the principle that information is preserved would be broken. So he began to estimate how much information a black hole could contain, and what he found was surprising. The amount of information did not seem to depend on the volume inside the black hole, the vast hidden region beyond the horizon, and instead it depended on the surface, on the area of the horizon itself. This is a very unusual result. In most situations, if you want to store more information, you need more space. A larger room can hold more books than a smaller one. A bigger container can hold more objects. We naturally expect information to scale with volume. But here, the pattern is different. It is as if all the information about what has fallen into the black hole is not spread throughout its interior, but instead is somehow encoded on its surface. You might imagine a shoreline. From a distance, the ocean seems vast and deep, extending far beyond what you can see. But the boundary, the thin line where water meets land, contains subtle traces of everything happening within the ocean, patterns of waves, shifts in colour, the gentle rise and fall of the tide. Now imagine that somehow all the information about the entire ocean, every current, every movement could be recorded along that shoreline. It would be a strange way to store information, but not impossible. And this is the idea that begins to emerge, that the surface of a black hole, the horizon, acts like a kind of record, a place where information is written, not in obvious symbols or structures, but in an incredibly fine, subtle way. Each tiny patch of the surface holds a small amount of information, and together, the entire surface contains the full story. This realization leads to a profound shift, because it suggests that the interior of the black hole, the region we imagine as deep and complex, may not be where the information truly resides. Instead, the boundary itself may be enough. This surface may contain everything, and if that is true, then something even more surprising follows. The idea that the three-dimensional space we imagine inside the black hole might not be fundamental, that it could be, in some sense, a reflection of information stored on a two-dimensional surface. It is a difficult idea to hold at first. We're used to thinking in terms of depth, volume, and interior spaces, but here we're being invited to consider something different, that the inside might emerge from the surface, that what appears to be a rich three-dimensional region could be described entirely by patterns written on a boundary. It is a bit like looking at a painting. At first glance you see depth, mountains in the distance, valleys, layers of space extending inward. But when you step closer, you realize that all of it is contained on a flat canvas. The depth is real in appearance, but the information that creates it lies on a surface. This idea does not only apply to black holes, it begins to hint at something much larger. If the information describing a black hole can be stored on its surface, then perhaps this is not a special case. Perhaps it is a general feature of reality. Perhaps in some deep and subtle way, the universe itself stores information on boundaries, and what we experience, a space, the vast three-dimensional world around us, could be a kind of projection emerging from those underlying patterns. This is not a conclusion, it is a direction, a possibility that grows naturally from the idea that black holes remember, and that their memory is written not in their depths, but on their edges. And as we follow this idea further, it begins to take on a more defined shape, because there is a framework, a way of describing this relationship between surfaces and volumes that brings all of these thoughts together into something coherent. A way of seeing the universe that suggests our reality may be more like an image than a container, more like a pattern than a place. And as we move gently into that idea, the horizon begins to feel less like a boundary between inside and outside, and more like a window into how reality itself might be built. If you remain with the image of a surface that can hold an entire story, something begins to unfold, slowly, almost like a thought forming at the edge of awareness. What if that idea is not limited to black holes? What if it applies more broadly to reality itself? It is a quiet step, but a profound one. Because if the information describing a black hole can be stored on its boundary, then perhaps the boundary is not just a feature of that object. Perhaps it is revealing something deeper about how the universe organizes information. This possibility was explored further by a physicist named Juan Maldacena, who proposed a remarkable idea that there can exist two completely different descriptions of the same physical system. One that lives in a space with gravity, where objects move and interact within a curved geometry, and another that lives on a lower dimensional boundary, where gravity does not appear in the same way, but where all the information is still present. At first, this sounds abstract, almost like a mathematical curiosity, but the implication is surprisingly simple. It suggests that what we experience as a three-dimensional world, filled with depth, distance, and motion, could be fully described by information arranged on a surface with fewer dimensions. Not approximately, not as a rough analogy, but exactly. Two different perspectives, both valid, both complete. You might picture this like a hologram. If you have ever seen one, you know that it appears three-dimensional. You can move around it, see different angles, experience depth as if the object were truly there. And yet, all of that depth is encoded on a flat surface. The information that creates the illusion of space is contained in patterns, tiny variations that, when illuminated in the right way, give rise to a fully formed image. The depth is real in experience, but it is not fundamental. It emerges from something simpler. This is the essence of the idea, that the richness of space, the sense of volume and distance, may not be the most basic layer of reality. Instead, it could be a kind of projection, a way of organizing information that gives rise to the world we perceive. This does not mean that space is an illusion in the sense of being unreal. It means that space may not be the deepest level of description, that beneath it there may be a more fundamental structure, one that is not built from distances and positions, but from relationships and information. In this view, the universe becomes something like a vast, intricate encoding, a pattern that can be read in more than one way. One way gives rise to the familiar world of space and time, where objects move and interact. Another way describes the same reality in terms of information on a boundary, without needing to refer to a volume at all. And both descriptions are equally valid. Neither is more real than the other. They are simply different perspectives on the same underlying structure. This idea can feel almost dreamlike, because it challenges something very basic in our intuition. We are used to thinking that what we see, the space around us, the depth of the world, is the fundamental layer, that everything else must be built upon it. But here, the suggestion is reversed, that what we see is an emergent picture, a meaningful one, a consistent one, but not the most fundamental one. It is like realizing that the surface of a painting contains everything needed to create the illusion of depth, that the mountains, the valleys, the distant horizon all arise from patterns on a flat canvas. And yet, when you look at it, the depth feels real. You can almost step into it. The same may be true of the universe. The depth we experience, the sense of space extending in all directions, may arise from patterns that do not themselves exist in space as we understand it. This is not a conclusion that has been fully proven in all contexts, but it is one of the most compelling directions in modern physics, because it offers a way to resolve the tension we encountered earlier. If information is stored on boundaries, and if those boundaries fully describe what happens within, then the apparent loss of information inside a black hole may not be a loss at all. It may simply be a change in perspective, a shift from one description to another, from a three-dimensional story to a two-dimensional encoding. And this idea does more than explain black holes. It invites us to reconsider what we mean by reality, to ask whether the things we take as fundamental, space, distance, location, are truly basic, or whether they emerge from something deeper, something quieter, something more abstract, yet more essential. As this thought settles, you may begin to feel that the boundary of a black hole is no longer just an edge. It is a hint, a suggestion that the universe may be built in a way that is more subtle than we once imagined, that what appears solid and continuous may arise from patterns of information, and that, in some quiet and profound sense, we may be living inside a kind of hologram, not a fragile illusion, but a deeply consistent, beautifully structured reality, emerging from something just beneath the surface. If you sit with this idea for a moment, that what feels like a vast three-dimensional world might emerge from patterns on a surface, you may begin to notice something even more subtle, a quiet question forming beneath it. If space is not the most fundamental thing, then what is? What lies beneath the appearance of distance? What gives rise to the sense that things are near or far, connected or separate? One possible answer begins not with objects, but with relationships, not with positions, but with connections. In the everyday world, we often think of distance as something fixed. Two objects are close if they're near each other in space, and far apart if there is a large gap between them. But in the deeper layers of physics, there are situations where this intuitive idea begins to soften. There are cases where two particles separated by great distances behave in ways that suggest a kind of connection, one that does not depend on the space between them in the usual way. It is not a signal travelling back and forth, not a force pulling across a gap, but a shared state, a relationship that exists regardless of distance. You might imagine two dancers performing a perfectly synchronized movement, even though they stand on opposite sides of a stage. Their motions are not caused by one another in the moment. Instead, they are part of a single, coordinated pattern. In a similar way, certain parts of the universe can be deeply connected, even when they appear far apart. And this idea leads to a gentle but powerful possibility that what we perceive as space, the distances between things, may arise from the pattern of these connections. Imagine a network, not a network of roads or wires, but a network of relationships, points connected by lines forming a web. If the connections are strong and dense in one region, that part of the network feels close. If the connections are sparse, it feels far. In this picture, distance is not something fundamental. It is something that emerges from how strongly different parts of the system are linked. Space then becomes something like a fabric woven from these connections. Not a stage on which relationships occur, but something that is created by the relationships themselves. This is a very different way of thinking. Instead of starting with space and placing objects within it, we begin with connections, and space arises as a way of organizing them. You might picture threads being woven together, each thread representing a relationship. Where many threads cross and bind tightly, the fabric becomes dense and structured. Where they spread out, the fabric becomes loose and open. The shape of the fabric is not imposed from the outside, it is built from the pattern of the threads. In this sense, space may not be something that exists independently. It may be something that is continuously formed, moment by moment, by the underlying web of connections. And this idea begins to resonate with what we have already seen. If information about a black hole can be stored on its surface, and if that surface can fully describe what happens inside, then the inside may be an emergent picture, a way of interpreting the information. And if connections between pieces of information give rise to structure, then those connections may be what create the sense of space itself. This perspective also offers a new way to think about what happens near a black hole. At the horizon, where information is encoded, the connections between different parts of the system may become highly intricate, dense, interwoven. And from those connections, the geometry of space, the curves, the distortions, the paths that objects follow may emerge. In this view, gravity itself may not be a fundamental force in the traditional sense. It may be a reflection of how these connections are arranged, a natural consequence of the way information is structured. This is a quiet but profound shift, because it suggests that the universe, at its deepest level, is not built from objects moving through space, but from relationships giving rise to space. from patterns of connection that create the illusion of distance, the flow of time, the structure of reality. It is a gentle idea, one that does not demand immediate certainty. But it invites you to look at the world in a slightly different way, to imagine that the space around you, the room you are in, the distance between you and the stars, is not simply there as a fixed backdrop, but is being continuously shaped by something deeper, something more fundamental, something that does not exist in space, but gives rise to it. And as this thought settles, it leads naturally to another question. If reality is built from connections, from information woven together in subtle ways, then how is that information preserved? How does the universe ensure that its story is not lost, even as it changes, evolves, and transforms? The answer may lie in a principle that is both practical and surprisingly elegant. A way of storing information so that it remains intact, even when parts of the system seem to disappear. A way in which the universe protects its own memory. If you stay with this image for a moment, the idea that space itself may be woven from connections, you may begin to notice something quietly reassuring beneath it, a sense that the universe, despite all its complexity, does not simply lose track of itself, that even as things change, disperse, or seem to disappear, something remains intact, a memory, carefully preserved, not in one place, but everywhere. In our everyday lives, we often store important things in a way that protects them from being lost. You might keep copies of a photograph in different places. You might save a document more than once just in case something goes wrong. The idea is simple. If one copy is damaged, another remains. The information survives. Now, imagine taking this idea much further. Imagine a system where information is not just copied, but distributed in such a way that no single piece contains the whole story, and yet the entire story can still be reconstructed from many different parts. It is a subtle kind of protection, not based on duplication alone, but on relationships between pieces. If one part is lost, the others still carry enough structure to recover what is missing. This kind of idea appears in modern computing, where information is stored in ways that allow errors to be corrected without losing the original message. But what is remarkable is that something similar may be happening in the universe itself. When physicists began to look more closely at black holes and the problem of information, they noticed patterns that resemble this kind of distributed storage. The information about what falls into a black hole may not be stored in one specific location. It may be spread out, encoded across the surface, woven into the relationships between different parts of the system. And because of this, even if parts of the system seem to disappear, falling beyond the horizon, becoming inaccessible, the overall structure can still preserve the information. It is not fragile, it is resilient. You might imagine a melody played by an orchestra. No single instrument carries the entire piece. Each one plays a part contributing to the whole. If one instrument falls silent, the melody doesn't vanish entirely. The remaining instruments still carry enough of the structure that the music can continue, and in some cases even be reconstructed. The information is not tied to one location, it is shared, distributed across the entire system. In a similar way, the universe may store its information in a way that is not dependent on any single region of space. This helps to explain how information could survive the extreme conditions of a black hole. Even as matter falls in, even as the structure we recognize disappears, the information may already be encoded in a broader pattern, one that extends beyond the interior. And as the black hole slowly emits radiation, that pattern can, in principle, be carried outward, not as a simple, readable message, but as a complex, distributed encoding. This idea brings a sense of continuity, It suggests that the universe does not simply erase its history, it transforms it, preserves it in ways that are subtle but consistent. And this perspective begins to tie together many of the threads we've been following. The idea that information is stored on the surface, the idea that space may emerge from connections, the idea that radiation carries hidden structure. All of these begin to feel like different expressions of the same underlying principle, that reality is built from information, not in the sense of abstract data, but in the sense of relationships, patterns, and structures that define how things are arranged, and that this information is not easily lost. It is protected, encoded, woven into the fabric of the universe itself. There is something quietly elegant about this. The notion that even in the most extreme environments, where gravity is strongest, where space and time are stretched to their limits, the universe maintains a kind of order, a way of keeping track, a way of ensuring that its story continues, even as its form changes. It is not a rigid system, not a static record, but a dynamic one, a memory that evolves, that shifts, that redistributes itself across space and time, and this brings us back gently to the larger picture. Because if the universe stores information in this distributed, resilient way, if space itself emerges from connections, if boundaries can hold the stories of entire regions, then the distinction between inside and outside, between surface and depth, begins to soften. What we once thought of as separate layers of reality may in fact be different expressions of the same underlying structure, and this realization opens the door to a final quiet reflection, one that reaches beyond black holes, beyond the edges of collapsing stars, and into the origin of the universe itself. Because there is another place where our understanding begins to blur, another boundary, not at the end of time, but at the beginning. And as we turn our attention there, we may begin to see that the story of black holes is not isolated, it is connected, part of a larger pattern, one that stretches from the deepest regions of space to the very first moments of the cosmos. If you let your thoughts drift outward now, beyond the quiet boundaries of black holes, beyond the faint glow of their fading light, you may begin to notice a gentle symmetry, a pattern that feels familiar, even if it is difficult to fully grasp. Because there is another place where our understanding begins to soften, another boundary where time behaves in ways that challenge our intuition, not at the end of time, but at the beginning. We often speak of the universe as having started from a single moment, a beginning so dense, so hot, that all of space and time were compressed into a state we can barely describe, a moment we call the beginning of everything. And much like the singularity inside a black hole, this beginning is not a place we can point to in space. It is a limit, a boundary in time, a point beyond which our current understanding cannot easily reach. In both cases, the center of a black hole and the origin of the universe, we encounter something similar, a place where our familiar descriptions begin to fade, where space and time, as we know them, no longer behave in predictable ways. It is tempting to see these as completely separate phenomena, one hidden deep within collapsed stars, the other stretched across the entire cosmos. But there is a quiet possibility that they are connected, that they reflect two sides of the same underlying structure. At one end, time seems to begin. At the other, it seems to end. And in both cases, our theories approach their limits. This symmetry invites a gentle question. If we want to understand how the universe began, perhaps we can learn something by studying how it ends. Black holes in this sense become more than isolated objects. They become windows, places where the deepest questions about reality come into focus. And unlike the distant beginning of the universe, black holes are not beyond our reach. We cannot travel to them, of course, but we can observe their effects. We can study the light around them, the motion of stars nearby, the subtle signals they send across space. In recent years, we have even taken images of their shadows, dark regions outlined by glowing matter captured by a global network of telescopes known as the Event Horizon Telescope. These images are not photographs in the everyday sense, but careful reconstructions built from signals gathered across the Earth. Still, they reveal something remarkable, that these strange objects, once purely theoretical, are real. They exist, and they behave in ways that match our understanding with surprising precision. We have also detected the gentle ripples that black holes create when they merge, subtle vibrations in the fabric of space itself, observed by instruments such as LIGO. These signals travel across vast distances, carrying with them information about events that occurred billions of years ago. It is a quiet confirmation that black holes are not just mathematical ideas, they are part of the living universe, and through them we are able to explore conditions that would otherwise remain far beyond our reach. As we gather these observations, as we refine our theories, the picture slowly becomes clearer, not complete, but more detailed. We begin to see how black holes connect different areas of physics, how they link gravity and quantum behavior, how they challenge our understanding of information, how they hint at a deeper structure beneath space and time, and perhaps most importantly, how they invite us to ask better questions. Because in the end, black holes do not offer simple answers. They do not resolve the mysteries of the universe in a neat and final way. Instead, they guide us. They point toward the edges of our knowledge. They reveal where our current ideas begin to stretch. And in doing so, they help us move forward. There is something quietly beautiful about this. The idea that the darkest objects in the universe, those that seem to hide everything, are also the ones that reveal the most. That by studying what disappears, we learn what remains. That by following the path of something falling inward, we begin to understand the structure of everything outward. As you sit with this thought, letting it settle gently, you may begin to feel that the universe is not a collection of separate pieces, not a set of isolated objects scattered across empty space, but a connected whole, a system in which information flows, transforms, and persists, where boundaries are not just limits but bridges, where endings reflect beginnings, and where even the deepest mysteries are not barriers but invitations. And so, as this quiet journey comes to a close, you're left not with a final answer, but with a softer understanding. That black holes are not just places where things vanish, they are places where reality reveals itself, slowly, patiently, and with a quiet kind of clarity. And so, we've reached the end of tonight's exploration. Whether your eyes are still open, or you're already drifting somewhere between waking and dreaming, you followed a path that began with a simple question, and unfolded into something much deeper. We started with the image of a dark object in space, a place where light cannot escape, and along the way that image softened. It became something more than a destination, something more than an ending, a place where time bends, where information lingers, where the surface holds the story of what lies within, and where the universe quietly hints that what we see may not be the most fundamental layer of reality. Perhaps space is not a fixed stage. Perhaps time is not a steady flow. Perhaps everything we experience emerges from something deeper, something woven from connections, from patterns, from relationships that extend beyond what we can easily see. It is a gentle thought, one that does not demand certainty, only curiosity, because the universe does not rush to reveal its secrets. It unfolds them slowly, in quiet moments, in subtle patterns, in questions that return again and again, each time a little clearer. And maybe, as you rest now, letting these ideas drift softly. Through your mind, you can hold on to just one feeling, that even in the darkest places there is structure, even in the most distant mysteries there is connection, and even in the questions we cannot yet answer, there is meaning. Time has a way of slipping through our fingers, but here, in this quiet moment, it slows, it softens, it becomes something you can simply rest within. Sleep peacefully, wherever and whenever you may be.